Good afternoon, everyone. Welcome to the Samvaad-Talk series organized by IIT Bangalore. On our theme, A Roadmap to 5G and Beyond Communication, today we have with us as the speaker, Professor Abhay Kumar Sah from IIT Roorkee. He is one of the prolific wireless communication engineers who is currently working as an assistant professor in the Department of Electronics and Communication Engineering at IIT Roorkee. Professor Shah received the B.Tech degree in Electronics and Communications Engineering from the Jaypee Institute of Engineering and Technology, Guna, in 2010, and the Ph.D. degree with the Department of Electrical Engineering, IIT Kanpur, in 2017. After Ph.D., he has worked at Samsung R&D Institute Bangalore as a senior lead engineer from January 2018 to September 2019, where he has been primarily involved for development of 3GPP Release 14 feature developments. Later, he worked at Radisys India Pvt Limited, Bangalore as a lead software architect and was involved in the PUSCH algorithm development for 5G base stations. His research interests are in realizing massive MIMO systems for next generation wireless technologies and in the applications of deep learning for wireless communication systems. He is a recipient of the DST-Inspire Faculty Program, TCS Research Fellowship, and the Vice-Chancellors Gold Medal for outstanding performance in his bachelor's degree. He is also a recipient of the Samsung Citizen Award for his contribution to standards during his stint at Samsung R&D. Today's talk is about intelligent massive MIMO for beyond 5G systems. So over to you, Professor Abhay.
Thank you, Professor Amrita, for the kind introduction. So this talk is about intelligent massive MIMO for beyond 5G systems. So as Professor Amrita already have introduced me, so just to quick story about me. So I am currently affiliated with IIT Roorkee and have 10 plus years of experience in the field of massive MIMO. And previously I have worked for Samsung R&D Bangalore and Radisys India Pvt Limited. And I have 15 plus journals and conferences on the same area and 10 plus patents on the related technologies. So let's start this talk. So in this talk, we will start with information theoretic motivation of massive MIMO system. Then we will see what is the role of a massive MIMO system in 5G system and what is the biggest deployment so far. And then we will answer few of the questions like what is the future of massive MIMO and what are the challenges. And then we will talk about the one potential solution, that is intelligent massive MIMO systems. And we'll talk about two such problems. One problem is denoising of the receive signal for any kind of signal processing after that. And the second problem is the signal detections. And finally, we'll talk about the takeaways and we'll take the questions and answers. So let's begin with, since the inception of wireless communication, the primary goal was to improve the capacity. The first wireless communication happened around 1887 or 1890 around. But the first formal characterization of capacity is established by Shannon after almost 50 years after that, that is in around 1948. So the capacity formulation is this is related with bandwidth times log 1 plus SNR. And so if a question can be asked that what should we do to improve the capacity? So there are two answers that we can do. That either we increase the bandwidth or we increase the signal power. But so let's understand that there are limitations. We cannot increase the bandwidth because the spectrum is scarce. And the second problem is that signal power is that increasing SNR also may not be a viable option. Why it is like that? So if you see here, let's say at 15 dB, we are having a 5 bits per second per hertz. The capacity is 5 bits per second per hertz, around 15 dB. When you go up around 30 dB, your capacity gets double, which is from 5 to 10. But how much extra SNR we require to double the capacity, which is 15 dB to 30 dB. So if you convert into a linear scale, 15 dB is around 31 and 30 dB is around 1000. So almost 30 times more power we require to achieve that much of capacity. So doing this way, like increasing the bandwidth or increasing the signal power, may not be a good, like feasible option. So can we do something else? The question was, can we do something else? So yes, we can do something else. That is, either we improve the spectral utilization, that is whatever bandwidth we are using, that can, if we can able to utilize in a better way, or we can improve the receive SNR without increasing the signal power. So, but the next question is how we can improve the spectrum utilization, or we can increase the receive SNR. So there are two approaches to do that. One approach is diversity, that we diversify the transmit signal. So increasing number of independent paths between the transmitter and receiver. So for example, here your transmitter having one number of antenna, but the receiver is having two number of antenna. So the same signal is traveling through two paths to the receiver. One is like from the antenna, the transmit antenna 1 to the receive antenna 1, and the other path is through this transmit antenna to the receive antenna 2. So this improves the SNR at the receiver without increasing the signal power. The other approach is spatial multiplexing, where we deploy multiple number of antenna at the transmitter, and there is a and we receive that signal. So the multiple antenna is used to transmit different data. So for any per unit channel, we can transmit multiple data streams, so that a receiver can receive multiple data, and through that we can improve the spectrum utilization. So this helps us to improve the spectral utilization. So these two, in any system, we cannot go with the maximum diversity, or we cannot achieve the maximum spatial multiplexing. So there is a trade-off, and that trade-off, if someone is interested, they can refer to this paper, the famous paper by Professor David Say and Professor Cheng, Diversity and Multiplexing, a fundamental trade-off in multiple antenna channels. This appears in 2003. But these two approaches give the basis for MIMO systems. So what is a MIMO system? We have multiple antenna deployed at the transmitter and multiple antenna deployed at the receiver. So using the Shannon's result, the capacity of a point-to-point MIMO system is derived as so there is one additional term, which is minimum of NT-NR. This is one additional term. The rest of the terms was same, that is bandwidth times log 1 plus SNR. So looking into this expression, it is we can observe that if we increase the number of antenna, the capacity can be improved. But the question is that, is it really that simple that we can increase the number of transmit antenna and receive antenna and increase the capacity? So the answer, we'll try to explore the answer. So there are certain limitations in deploying many antennas. So the first limitation was that there was no requirement to have more number of antenna at the initial days. Let's understand this by an example. So assume there is a network provider which sells three kinds of service data packs. One supports 10 Mbps of average data rate at 100 rupees per month. The second choice you have that 1 Gbps of average data rate at 500 rupees per month, and the third one is that 1 Tbps of average data rate at 2000 rupees per month. The question is, which one you will consider buying? The answer would be, the most of the people will settle on option A and or B. Like there will be hardly any people who will consider option C. The reason is that at today there is no such application that requires a 1 Tbps of data rate. So people will not go for that. Most of the people will settle for A and B. So that was the first limitation. Since there was no requirement, there was hardly any study on this. That what I mean by study, that we are not sure how the capacity will behave if you are going for a very large number of antenna. So for a small number of antenna, it's okay that it will scale linearly with the number of antenna. But what happens if the number of antennas are 10, 20, 100, 1000? Will it remain linear, or so that there was hardly any study on this. Then there were certain implementation challenges. The implementation challenges was like use size. So what we mean by use size, the minimum separation between two antenna needs to be lambda by 2. And if you consider a 1 gigahertz of operating frequency, the minimum separation would be around 16.5 centimeters. So thus, if you are planning to deploy your 8 antenna, you will require a transceiver of size of 1 meter. So which is not practical for many devices. Second, the complexity in signal processing. So as you deploy more number of antenna elements, it is true that capacity is increased, but that capacity must be supported by a decent signal processing algorithm, like how you will perform a signal detection, how you perform the pre-coding, how you perform the channel estimation, how you perform the pilot contamination. So all these problems were there, and initial days we are all stuck into the all these problems. So all the initial research was primarily focused on solving for a smaller number of antenna for these kind of problems. So we haven't thought about solving such problems for higher number of antenna. Then there was a high cost, because what I mean by high cost, that every antenna needs to be supported by a dedicated RF chain. So RF chain are the elements that transfers a baseband signal to a passband signals and used for the transmission or reception of any signal. So RF chains are usually quite costly in terms of money as well as power consumption, both. So a high power consumption will lead to a poor energy efficiency. So this was one bottleneck. People may not, like in initial days, people have not even tried for going for high, like more number of antennas. So thanks to all the efforts made by research community, so whatever all these issues are addressed, and there are several efforts made to realize a massive MIMO system. The first envisioning of the requirement for massive MIMO appears around 2008, like when Professor Chokalingam from ISC, he started off proposing systems which has a 32 antenna or 64 number of antenna, like that. But the first a formal study on a very large antenna system was done by Professor Marjeta around 2010, and in this paper he shows even for infinite number of antenna, the capacity scales linearly, and for this work he received the highest IEEE award, that is a Baker Award. This is the award given for among all the IEEE societies. And for implementation, like the issue was the huge size, but at the so there were several work which explores high dimensional array, like from linear array to planar array to three-dimensional array. So that we can compactly pack more number of antenna in a same for a limited area. Second, we are starting looking for higher operating frequency. So higher operating frequency means like millimeter wave, where your wavelength is going smaller and smaller. So the requirement of lambda by 2, which is required for between two antenna elements, is getting lower and lower. So that also helps for going for a larger or high number of antenna elements. Then complexity in signal processing. So there are several works addressing different problems like signal detection, channel estimation. This is one good review paper that I have highlighted. So this gives quite a detailed summary of all the works that happens, especially for pilot contamination, channel estimation, and signal detection. For addressing the issue of high cost, there are works which talks about even if you increase the number of antenna elements, you do not need to increase the number of RF chains, and we can beam form or beam combine the data. So beamform is used for at the transmitter side, and beam combine is used for the receiver side. So you have a multiple data streams, but they are supported by only a fewer number of RF chains, but a larger number of transmit or receive antenna elements. And this is one of my work which is published, which is basically around for beam combining, keeping the Massimaimo receiver side where a large number of antenna elements is used to receive the signal, but there are very few number of RF chains, and we are able to show that even like around 8:1 ratio, you are able to achieve a similar performance what we can achieve through a full or dedicated RF chain systems. So all these efforts make somehow make the realizing Massimaimo for the upcoming 5G systems. So there are two realizations for Massimaimo. One realization is large MIMO. When we talk about, so this was a kind of extension of point-to-point MIMO. Means you have multiple antenna at the base station, multiple antenna at the user side also. But this realization has very limited scope because it's still base station has a use side and we can deploy a more number of antenna. But at the receiver side or the user side, the size of device is quite small, like a mobile phone. Still, you cannot deploy so many number of antenna. So the scope is very limited. Like you can use large MIMO for base station to access point kind of communication, but not in a generic way like user to base station kind of a communication, a mobile user to a base station. So the other so this work was published around in 2008, and there are several work followed after that. And then to Massimaimo is the other realization, which I should say that it's more practical realization of this large MIMO, where it is assumed that there are multi-users in the system. So base station is equipped with a large number of antenna, but there are several mobile users. They are concurrently transmitting with the base station. So what happens at a larger front, they act like the different antennas are located at different places with some with satisfying this λ/2 constraint. So mathematically, there is no difference between large MIMO and Massimaimo. It is more about the implementation. So one is a point-to-point MIMO like realization. The other one is the extension of that same thing for a multi-user setting. And in a typical world, there will be always there are several users. They are trying to access the base station. So this is more practical. And therefore, it is part of all the recent wireless standard. Whether you talk about 5G, whether you talk about the Wi-Fi standard, the 6th generation Wi-Fi standard, or you talk about any other kind of like wireless standards. So Massimaimo is getting into all such wireless standards. Okay, so so this is all about the journey of Massimaimo. But what is the role of Massimaimo in 5G? So 5G, Massimaimo is considered one of the key pillars of 5G. So, but the role of Massimaimo in 5G is to support EMBB use case. So what is EMBB? It is enhanced mobile broadband. So basically to support a high data rate scenario, but it is not only designed for EMBB case. It can support the other two use cases, URLLC and the MMTC case, but we are not talking about that. We will keep focus on the EMBB use case because it is primarily designed for that. And the 5G realization of Massimaimo is not about improving the throughput or the data rate via conventional ways, that is using spatial multiplexing. In fact, it is about to implement beamforming. Why I am saying that? Let's give me one explanation. So this is a conventional data flow in a 5G system. So if you notice here, there is a block called layer mapper. So this block is in the 5G literature, we call it the layer mapper, but in a theoretical way, this is the block which is doing the spatial multiplexing. And as per the standards, there are up to only 8 spatial data paths we can allow. So the maximum number of parallel streams that can be allowed is 8, and which is same as 4G. So there is no increase in the spatial multiplexing gain of the 5G system compared to the 4G system. But still, we are implementing Massive MIMO. This is through the beamforming. So here you can see there are red blocks, 2 red blocks. This is WBF and the BF. So these are the 2 components. One is called analog beamforming and the other one is called digital beamforming. So let's talk about what is a beamforming in 5G. So beamforming, it is something like that. Let's say if you are talking with some person, what is the best way to talk? It is communicating face to face. So if you want, so it is like, so if a person is sitting next to you, you will slightly rotate and you will talk to them, him or her. So the same thing in antenna also, we can rotate the antenna physically and align with a particular user. But this is not a feasible option for all kind of settings, because usually users are located in all directions, so you cannot align only to a particular user. And also, like rotating a antenna physically is not always a feasible option. So what is the smarter way? If we can control the phase and amplitude of the signal. So how we can do that? So here you can see that there is a one signal ST, and this signal we want to transmit. And then there are phase controller and gain controller. So the same signal, there are different copies of the same signal. S1T will be a copy of ST with a phase theta1 and gain W1. Similarly, there is another signal S2T which will have phase theta2 and gain W2. And similarly, we will have total in this diagram, there are total 8 gain controller and total 8 phase controller. So the equivalent signal can be expressed mathematically as it is a sum of all these 8 copies, which is W1 EJ d theta 1 plus W2 EJ d theta 2. D is the separation between the two antenna elements, and ST is the final signal. Okay, so it will be able to generate a single beam, something like this. Okay, so in a single beam, how many users we can support? We can only support those users which are inside this beam. If a user is sitting somewhere here, how will support that? We cannot support using the same architecture to this user beam. Why? Because we need multiple beams. So what should we do to generate multiple beams? So to generate a multiple beams in 5G, the idea is to do a digital pre-coding and followed by analog beamforming. So this is one architecture that describes that. So between the digital beamforming and the analog beamforming, so we have a KT data streams and there are NT number of transmit antenna. So this KT data streams is first digitally pre-coded and then it is transmitted to the through the RF chain, and then it is analog beamforming is performed, where different number of phase shifters and different number of adders. So phase shifters you can think like it's a phase controller, and these adders are the gain controller. So finally, whatever signal we are receiving, we will have it here. We will transmit through these antenna units, and so with the help of these gain and phase controllers, we will be able to form multiple beams. So large number of antennas are used. So if you increase the number of antenna, you will be able to form a highly directional beams, which helps in improving the SNR because now your entire energy is concentrated in a particular beam. So the receive SNR will improve. That was the initial aim that we have talked about. And it will also avoid interference, because if you have a bigger side lobe, so there will be different kinds of interference. If you have a narrow beam, your interference levels will be low. So that will again help in improving the SNR, the signal quality, which will result in an enhanced throughput experience. So this was the way the Massive MIMO is being implemented in 5G system. And the biggest realization that has been done for Massive MIMO for 5G systems is it has been done at the Lund University and the Bristol University. In this, you can see that in this diagram, like a 120 number of antenna elements are used. So you can see here, there are 4 stacks. In each stack, there are 8 antenna elements from vertical direction, and there are 4 antenna elements in the horizontal direction. So 32 antenna elements in each stack. So 32 antenna elements in each stack. So that will give us total 120 antenna elements. The operating frequency that has been considered is 3.5 gigahertz. Bandwidth, the chosen bandwidth is 20 megahertz, which is same as 4G system, although 5G allows a bandwidth up to 100 megahertz. Modulation scheme also like 256 QAM, which is the highest modulation scheme supported by 4G system. So if you see, except the operating frequency and the number of antenna, all the other system parameters are keep same as 4G system, so that we can compare both the systems, the gains of the systems. So the achieved spectral efficiency for this system was 79 bits per second per hertz if there are 12 number of users. But as we increase the number of users to 22, so the spectral efficiency improves from 145 bits per second per hertz. So to just mention about this number, so this is like if a 20 megahertz system, we need to multiply by 20 megahertz. So we will get the total data rate in terms of, so which will roughly around 3 Gbps. So this much is the biggest realization that has been done. And there are in the current market, there are almost close to 50 plus products that are available with Massive MIMO technology, varying the number of antenna. There are some products with 16 number of antenna. There are some products with 32 or 64 number of antennas. So it becomes a reality in current world. But what is the future? The next question is, what is the future of Massive MIMO? So one future is that we know that spectral efficiency grows monotonically with number of antennas. So we can keep on increasing the number of antennas. So we expect a future where thousands of antennas are used to serve a set of users. So how we can do that? Because no matter like whatever physical structure you will use, there will be always some constraint, and you won't be able to deploy more than a certain number of antenna. So there are currently there are 2 possibilities. One is co-located arrays. So co-located arrays are like you can imagine a roof tower, a rooftop of some building or high-rise building. There are certain antenna elements. So there are we deploy certain number of the antenna elements, and they are co-located. They are connected to a CPU here, which is sitting adjacent to all these antenna elements, and these will act like a big surface, and where we can deploy more number of antenna. The other is that we use extremely large aperture array. What I mean by extremely large aperture array, the entire building we deploy, like here you can see this wall in the option B. You can see this entire wall. There is there are windows, and each window we have placed all the corners of windows we have placed the antenna elements. So, and this is a kind of a very extremely large aperture. So like maybe you can think of a 20 floor building, high-rise buildings, and entire building is acting like a base stations. So, so this is like one kind of extension of the current Massive MIMO system. The other extension is that we deploy the massive, like all these antenna across the entire very large geographical area, and they are all connected through some optical fiber cables through a central processing unit. So you can imagine a city like Bangalore. There is a one CPU where and there are only antenna elements spread across the city. So maybe every 10 meters you will see another antenna element. So there is a paradigm shift. What is that paradigm shift? That currently a tower, a base station is surrounded by several users. And self-free Massive MIMO, the aim is to reverse that. A user will be surrounded by so many antenna elements. So there will be some antenna that can serve, or there will be at least more than one antenna that can serve that particular user. So this concept is that called as self-free Massive MIMO system. So that is also being considered as one future extension of Massive MIMO system. There is another extension which is holographic Massive MIMO. The idea is to integrate an uncountably infinite number of antenna to a limited surface area. So basically, we need a continuous transmitting and receiving aperture. So so this requires radically new way of designing antenna arrays, and obviously we should not call this an array because these are not discrete elements; these are the continuous element. And in the research in this direction are taking place under the names of holographic RF system or holographic beamforming. And there is another class which is large intelligent surfaces, which is also part of holographic RF system. But in this, we are still using a discrete antenna elements rather a continuous antenna elements. So the idea is we have a surface, we can call this a meta surface, which has a radiating element, and it is connected to an RF signal generator. So whatever RF signal is generated, it will pass through this surface, and it will diversify that signal, or it will beamform according to the user's position to a particular direction. And it will, so this is one way to implement that. The other way, you probably have seen this, the other example in many contexts, like intelligent reflecting surfaces or RIS, or there are different, or IRS, there are different names for this. So there is a base station which is transmitting a signal to a meta surface, and meta surface is now just acting like a mirror, and a mirror which is an intelligent that can reflect that particular signal in the direction to the desired user. So these are the few example extensions of Massive MIMO systems. There are certain kinds of challenges involved. So the first challenge is that almost all the problems that are being addressed for Massive MIMO need to be reinvestigated. What I mean by that, like channel estimation, signal detection, beamforming, because your dimensions, you are going to a higher dimension, you are going to co-located to a decentralized Massive MIMO in the case of self-free Massive MIMO. So all these problems need to be reinvestigated because the conventional algorithm may not be suitable to handle the delay constraint, the latency constraint, or the complexity will be too high. So we need to address those. And also, given their nuance, several new problems need to address. For example, in self-free Massive MIMO, there are so many antenna elements. So the coordination needs to be there between those antenna elements, and they are located at distributed different places. Similarly, the meta surfaces, the reflecting surfaces needs to be controlled, and that control should be from the base station. And so all these problems needs to be addressed, and the biggest hurdle in addressing these issues is their intractable model, because the dimensions are so high. If you go with the conventional method, you may not be able to turn up in a given time constraint. So therefore, we need a system which is intelligent enough, and therefore the term is coined as intelligent massive MIMO system, and it is the way forward. So the next part, you can refer these two papers if you want to study more. The first paper is from Emil Beersen, and the second paper is from on deep learning for physical layer, for 5G wireless. So machine learning is especially powerful when the system characteristics are hard to model. So whenever there is some system which is intractable, machine learning algorithms can really help us. We have seen in different use cases. Thus, we expect ML will also play an important role here. And few of the problems are highlighted here. The first problem is that optimal array placement and configuration. What I mean here, that if you remember the extreme large aperture array, where the antenna elements are placed at the roof of a high-rise building. So assume that there are these antenna elements are placed in a railroad, and we want to move, or we want to turn, so that we can optimally support different users. We can overcome with any kind of shadow or any kind of that. So in that case, we need an ML based algorithm by which we can adjust the position rather than relying on a conventional signaling, which will not fit into this case. The second problem is ML based channel estimation. So conventionally, how the channel estimation is performed, we have a pilot signal. That pilot signal is being transmitted to the base station, and through that a signal, the base station acquires the channel state information. Now you imagine the cases of extremely large aperture array or cell-free massive MIMO, where so many antenna elements are there. The number of pilots is going to be very scarce, or the problem will be that there will be a huge amount of interference, and the conventional model will no longer will able to give you the good enough quality of channel estimate. So again, we expect that machine learning can play an important role here. The third problem is that how we can configure the meta surfaces. These meta surfaces can use the channel chart positions, which they can learn through the users, different locate, where is user located, what is the user's velocity, and other thing. And based on that, it can help to redirect the signal received from the base station. The fourth problem is that handovers. Handovers are usually what happens, how handovers happens, that whenever a person moves from one base station, there is a one signaling broadcast, that is a broadcast message goes to all the neighboring base station that this person is moving, and they are trying to support them, and there is a lot of signaling happens in the background. But in day-to-day life, if you think that you are going from one position to another position, we have almost fixed trajectories. Let's say someone is moving in outer ring road. So if he moves from one place to another place, we know what are the different base stations that can support a particular user. So if a user is moving in a particular direction, no need to do all those signaling. Instead, we can have a machine learning algorithm that can directly transfer the signal from one base station to another particular base station, learning the movement of the particular user. So all these kinds of problems can be addressed by machine learning for systems, algorithms. And the fifth and the last but not the least is that we can design baseband signal processing algorithm augmented with the machine learning. So machine learning can be used to define almost any part of a conventional Massive MIMO system and turning them into an intelligent Massive MIMO system. So we'll talk about two such problems. The first problem is denoising for signal processing. So what I mean by denoising, so denoising, it is a process to remove the noise from the original signal. So usually it is an iterative process is followed that is summarized as. So in step 1, we have a channel estimation. First step is that we perform a channel estimation using the receive signal. So we have a receive signal, that is the raw receive signal, and then we perform a channel estimation. In the second step, since we know the channel estimate, we can now estimate the noise. So we use the channel estimate to estimate the noise. In the third step, we this estimated noise is subtracted from the raw receive signal. Okay, so once you subtract, you will get a denoise signal, and that denoise signal is again used for repeating all the steps 1, 2, and 3. That is again performing channel estimation, noise estimation, and denoising the signal. So it is a kind of iterative process. And after a few iterations, we are able to get a good channel estimate and denoise the signal sufficiently, the received signal. So what is the significance to this denoising to the Massive MIMO system? The significance is that in a multi-cell Massive MIMO, there would be a pilot contamination, and the amount of noise in the future Massive MIMO, where you have even more number of antenna elements, this is going to be higher and higher. So we need a denoiser at the very beginning of any signal processing chain, and that denoising technique would be must to maintain the quality of your channel estimate, and that will lead to the quality of your final detection. But the conventional approach may not be a suitable or a feasible option for future Massive MIMO system, because it requires a lot of iterations. You need to do several number of times the channel estimations, and that will delay the whole process. So we expect the ML can play a decent role. So the methodology we adopted, what we observed, let's see, this is an image, which is you can see the left image is the original one, and the right image is the denoised image. And so what the denoising has done, it has like all the pictures, you can see that the quality of picture has improved a lot. The images are sharp now, even the water shades are very clear and crystal. So this denoising is remove the noise from these original signals, and we observe that this kind of technique is quite common in image processing literature, and there exists a handful of DNN based algorithms for achieving the same. So we explored that, and we observed that there are two such algorithms that have been recently used. One is deep decoder, and the other one is deep image prior. So in this work, we have used deep image prior based denoiser method that do not require multiple channel and noise estimations, and also it is not required training. That is also very crucial. Like almost all kind of DNN networks requires a certain kind of a training. Like you have to train the data on certain kind of data set, and then only you will be used to. And if you change the data set, probably that will no longer the same model you can use. You have to train it again. But the beauty of the DIP is that it learns from the data, like whatever data you will feed, it will learn from that itself. So we have used this denoise signal for channel estimation. So So this denoise signal can be used for signal detection and other purposes also. In our work, we have used for channel estimation. So instead of the raw received signal, we have used the denoise signal and we perform a least square channel estimation, which is the simplest channel estimate. If you compare with the other algorithms like MMSE, the least square is quite simple. And we compare the normalized mean square error for the following system configuration. So what system we have considered? An uplink system which has a bandwidth of 20 megahertz, 128 antenna elements. It has 64 subcarriers. Coherence time we have assumed that 64 RDM symbol, and there is an interference of 10 dB. And the pilot contamination, we have assumed that there is a random pilot contamination. So the simulated result, you can observe here that the topmost is the least square channel estimate, that is the blue line. Then we have MMSE channel estimate, which is the red line, and the yellow line, which is the bottommost, is a Gini added channel estimate. This is just a reference line. This is the best we can do, we can achieve. And in between, you can see there are two algorithms, which is one is deep decoder based channel estimate, and the other one is the purple line is with the DIP based channel estimate, and which performs significantly better than LS, not only with the LS but also with the MMS. Okay. So the second problem that we have worked on is DNN based signal detection. So we have used deep neural network for performing a signal detection, and we consider a spatially modulated Massive MIMO system. So what I mean by spatially modulated Massive MIMO system, so if you have information bits, like you have here, the information bits are 0, 0, 1, 0, 0, 1. So the first two bits is 0, 0, which is this, is used to decide which of the antenna will be active. Like there are 4 antenna in this example, not all of them will be active. There will be only 2 antennas are active. So if you see the table above, so 0, 0 map to 1 and 3. So first and third antennas are only active. So okay, so you can see here there are arrows between the transmitter side and the receiving antenna. The arrows are only between the first and third antenna, right? Then the remaining bits, like what are the remaining bits? 1, 0, 0, 1. So 1, 0, 0, 1 is mapped through the conventional 4-com constellation, which is 0, 1 is mapped to -1 -I, 1, 0 is mapped to 1 -I. So these two are the conventional symbols that are being transmitted through these two active antenna. Okay, so the challenge is to detect this signal at the receiver side. How you will detect? The conventional approach said that we will apply a maximum likelihood detection, where we will find the Euclidean distance between the received signal minus HI. I represents the antenna elements. So we'll assume that first 1 and 2 is active, then we'll assume that 1 and 3 is active, then we will assume 2 and 4 is active. So likewise, we will assume all the antenna patterns, and we will multiply with the all possible symbols. Like in this case, there are 2 symbols. So how many possibilities? So the possibilities will be there are 4 into. So there will be like 2 antennas. So everywhere, so 2 places. So 4 possibilities are there. So 4 possibilities here, 4 possibilities here. So total 16 possibilities are there. So for such a small system, now see this will have 16 possibilities, and the first one will have 4 possibilities, 4 antenna patterns. So 64. So for such a small system, 64 comparisons are required to know which bits has been transmitted. Now you extend this problem for a really large system where 128 antenna, let's say 16 active antenna or 8 active antenna. This problem will become very complex, and it cannot be solved in real time. So So the computational complexity is too high, and it depends on the channel matrix, which is again is intractable for really a massive MIMO system. So what we have done, we have divided this entire problem in two parts. First part, we started learning the model. The received signal is generated through the conventional way and under different channel state informations. And then we obtain the feature vectors. Feature vectors are kind of an input to our DNN model, which is received signal and the channel characteristics. We feed them, and we again generated a hot vector. Hot vector, it is a mapping from an information symbol to an indicator function. So all these 4 bits, like all of them, we map it to a hot vector. Like if let's say if there are 16 possibilities here, 16 QAM, or sorry, this is an example of 4 QAM. So let's consider 4 QAM. So we'll have 4 hot vectors like 1 0 0 0 1 0 0 0 0 0 1 and 0 0 sorry 0 0 1 0 and 0 0 1. So there will be 4 vectors, and they are kind of indicator functions. So we have a, so if we are able to decode this, which will again map back to the actual constellation point. So that is the idea of a hot vector, and the feature vector is used as an input, and the hot vector is used as an output to the for training the model. So this is the first part. We have trained the model. In the second part, the application phase, once the model is trained sufficiently, the output generated by the DNN is used to recover the input signals. So we have so far we have done it for very like not a very big system. We have only considered a transmit antenna 8, and the active antenna is 2, and constellation size is 16. And the training data size is also 20,000 only. And the total number of input nodes are 2 times n plus n into NA. N is your number of receive antenna, NA is number of active antenna. Hidden layers are 3, and the activation function we have used is ReLU and soft, that is for hidden layers, and softmax for the output layer. And the optimizer we have used is SGD. So here you can see that the block, this DNN, this block-based DNN method is in fact performing better than ML detection. So if you compare all the conventional algorithm, they are trying to just meet this boundary, this blue line. But this block DNN, which is very early simulations, we can see that this method can outperform even the conventional method, that is the ML detection. So the key takeaways of this talk, that we have seen what is the motivation for Massive MIMO system, how it can improve the capacity and throughput. We have also understand the role of Massive MIMO 5G, which is primarily for to support enhanced mobile broadband use case. The third is that we have seen the biggest realization of Massive MIMO is up to 128 antenna, and in the market there are several products exist of the order of 64 antenna roughly. The extension to ultra Massive MIMO, we have seen the Massive MIMO is being scaled to an ultra Massive MIMO system where there will be extremely large aperture will be used. We are going from a co-located Massive MIMO to distributed Massive MIMO, where the antenna elements will be placed across the city, and maybe 10,000 or 20,000 antennas will be placed across the city. Then we have also seen a holographic Massive MIMO can be a future extension, where instead of a discrete antenna elements, we will use a continuous aperture. The challenges involved is largely intractable models, and the one solution is intelligent Massive MIMO that can exploit machine learning techniques and try to bring intelligence to the Massive MIMO for the signal processing and to handle different kinds of problems in realizing all these future extensions. So with that, I'm concluding this talk. So thank you everyone for listening and patiently listening this talk. I will be, if you have any query, any question, you can ask me, and you can also reach me out on my email ID and my phone, and for more details you can go through my website. So if you have any query, please ask. Professor Amrita, you can.
Yeah,
Please.
thank you, Professor Abhay, for this extremely interesting and relevant talk. So we have a couple of questions on the chat. So I'll be taking them one by one. So the first question is by Professor Priyanka. Professor Priyanka, would you like to unmute and ask?
Thank you, Professor Abhay Sah. This is extremely important topic to all of the faculties and the students as well. So I have the question. You showed the first beamforming slide. No, I think it is initial 5 to 6 slides. You showed the beamforming. Right. Yes. So can you please go back? So my question is, how many beamforming can we provide by this technique?
Yeah.
Yes.
Yeah. Sorry. Can you say again?
So how do you control the directions of the beams for covering more number of users?
Okay, so it is basically depends on the channel estimate only. So the transmitter should know some sort of channel state information. Based on that, it will change the phases of like all these gains and phase controller, and accordingly it will form a beam. So that is the conventional way we follow for beamforming.
But at the same time, we can do only one beamforming, is it? If I
Right. Yeah, you are absolutely right. Like in this architecture, what I am showing here, we can only form a single beam, and therefore we need something like a hybrid structure where we have a digital beamforming and we have analog beamforming. So we have different data streams. So these data streams may be for different users, and like it's a multiplex data, and here we have different gain controller. Like if you see the first antenna is added like to the RF chain 1 is connected with the first NT times this total K NT phase shifters, and the bottom we have total again NT phase shifters. So these phase shifters, if you can change the weights depending upon the channel, whatever channel information we have, so we will be able to form multiple beams so that we can support different users.
And what is the difference of digital and analog beamforming? Can you just elaborate a bit detail?
Okay, so digital beamforming, it is the same as the pre-coding we touched. Like you have a weight matrix and you have a parallel data streams. So it is kind of these data streams are multiplexed here, and we are passing through the RF chain. Analog beamforming it is more about concentrating the energy to a particular direction so that we can support that particular user.
So both are essential to do.
Yeah, those are essential to do. So digital beamforming is primarily for achieving the spatial multiplexing gain, and the analog beamforming you can think of it is primarily to achieve a better receive SLR.
Okay, fine. And you talked about denoising. So you told denoising application is for channel estimation.
No, I have implemented for channel estimation.
What are the other application, Professor?
Okay, so basically the idea is to remove noise from the receive signal. So once you have removed the noise from the receive signal, the same signal can be used for detection. The same signal can be used for other purposes, whatever different kind of signal processing we do.
Okay, thank you.
So channel estimation is just one example.
Okay, thank you.
Yeah, thank you, Professor Priyanka.
Thank you.
Thank you, Professor Priyanka. So, Professor Abhay, we have the next question by one of our postgraduate students, Pratyusha, in which she asks, with respect to the cell-free Massive MIMO architecture, wouldn't it become a problem if the central CPU node is down? Can there be a distributed system better than the centralized one?
So my answer would be yes, but do not see this selfie Massive MIMO like whatever whatever this figure, it is just for an illustrative example. Like there is a CPU which is connected. Now, since the question is very rightly said, if the CPU is down, so the entire city will be like there won't be any connection. Like one base station is going down, like maybe you will have another base station in the city and you will get some partial support, or maybe at least other parts of city will not be disturbed. But in this case, if we are completely dependent on that particular CPU, but the today's world of cloud computing, like we are going from, I don't know whether you know the words, like virtual RAN. So it is like the radio access network where everything was sitting in that particular base station. In the virtual RAN or cloud RAN, we are moving everything to the cloud. So definitely the CPU will have enough resources, we are assuming, that it can support all those problems. Like one CPU is going down, then maybe there will be some backup or something like that. But the thing is that your cost of infrastructure will come down. You no need to deploy so many different, you have to manage only one central point.
So Abhay, so we'll move on to the next question by Neeta, one of our PhD students, in which she asks, multiple parallel transmission using hybrid beamforming can increase the side lobe interference levels at point of interest with respect to the user equipment. So what will be the impact of this side lobe interference on SNR? That is, the radiation pattern or beam formed will be different.
Okay, so it is if we are doing only one-way beamforming, like let's say transmitter is doing the beamforming, definitely if there are multiple beams, it is possible that there will be some kind of a side lobe information. But you need to understand there are two concepts. First, we are talking about once we'll go from the 5G, this beamforming is almost like for millimeter waves. So the beam width will be very narrow. It's a very narrow beam. So there are very low probability that it will interfere with the other beams. Second, all these beamforming should be complemented by receive beam combining. So the receiver should also do a beam combining so that it can align with that particular beam. So what will happen if one beam is aligning with the particular beam, the other beam will be almost in the null space to the other beam. So hardly there will be chance of such kind of interference that we are talking about. The probability is quite low.
Ma'am, can I ask?
Sure, Neeta, please go ahead.
Sir, actually, when we are transmitting signals, means parallel transmission, the side lobes will be smearing to the main lobe directions. So my question was whether this side lobe is smearing to that half power beam width that we are focusing towards our user will have a significant impact, because we have very narrow beam with very precise estimation of UE location. So when this multiple beams are transmitting, so that particular multiple transmission of that sum of side lobes, when it is smearing to that area of interest, what will be the consequences? So that was my question, sir.
I don't think I got your question rightly. I think you are asking if you have multiple beams, so how many beams you are considering?
So maybe four beams we are considering. So one is our main direction, and then
main direction, right?
Yes, and three that side lobes which is having an impact at that UE location. So whether it would be that much significant, that because that
I don't think it would be that significant. see, you have to consider the distances also. Like the area is roughly around 200 meters or 100 meters of size. So
Yes.
whatever you are saying, the side lobe, it is like very close to the base station. But as you increase, the difference between these lobes will be significantly high. And if you see the null coming, like there is one lobe, there is another lobe, the null will coming very sharp. So there will be hardly like any kind of interference coming from this because of this beamforming. Basically, the idea is to reduce all such kind of interference so that we can improve the receive SNR quality.
Okay, sir. Thank you so much.
Yeah.
Professor Abhay, we have one final question in the chat box by Professor Prasanna. He wants to know your insights with respect to the relation of deep learning with turbo codes and generalizations, if any.
Okay, deep learning with turbo codes and what is the second part?
The second part is if there has been any generalization, as per my understanding, is there any generalization with respect to deep learning applications in turbo codes?
Fairly speaking, I haven't explored much about turbo codes, like how deep learning can play a role to decoding turbo codes. But what I believe, definitely it can like usually we use kind of like BCGR algorithms and other things. Definitely turbo a deep learning based decoding can be used to complement the turbo encoding. I think there are some literature in auto encoders that is basically designed to especially suits all kind of encoding and decoding processes. So I remember there was one work where they have shown that it can perform slightly better than the turbo code decoding. But I'm not very sure about how it will.
Professor Abhay, I think I understood it, the question incorrectly. Professor Prasanna, would you like to unmute and go ahead?
No. See, Kohler Friedman mentions graphical models as being inspired by turbo codes, and actually turbo codes, the whole graphical model tree, belief propagation as being the same as turbo codes, or being inspired by, not being inspired by, but being essentially pushed forward by the success of turbo codes. So now deep learning is essentially a generalization of belief propagation. So has there been, how much work has there been to sort of push turbo codes forward, or can we regard deep learning methods themselves as essentially turbo codes with much more structure imparted to the signal?
Okay. Sorry, Professor Prasanna, I did not get your question exactly. I understand what.
All you have is turbo codes are essentially a special case of graphical models, and the derivative and the detection is a special case of the general belief tree propagation. I don't remember the details. So what I'm saying is, so since turbo codes are a special case, deep learning is basically a more generalized version of essentially more larger version of belief propagation. So equivalently you can improve turbo codes using deep learning. You can put more structure in it, more information.
Right. Okay. So I think you want my opinion regarding that, right?
Yeah.
Okay. So yes, it is true that the whatever DNN architecture we are talking about, it has similarity with the turbo code, like what the belief propagation and that way. And definitely the way forward, like one of the approaches is model-based deep learning, like where we keep our whatever understanding we have about, because in entire wireless communication, so far all the all are like based on the well-established maths. like zero forcing receiver, MMSC receiver, or whatever. All these are well defined by the well-established lab. So if you are able to keep all this like understanding of our model, and then we plug do a modification on DNN or deep learning architecture, that would be more suited for wireless communication. And there are people who are working on the similar direction. I know, but I haven't done much to that.
Okay, all right, thanks.
Yeah, thank you.
So, Professor Abhay, we have a question from Dibakar, one of our postgraduate students, with respect to how is the performance of beamforming for high-speed mobility? Any studies?
Okay, I have seen one paper. If you are really interested, you can drop me a mail. I will forward that. They have especially designed beamforming trains for high speed, beamforming algorithms for high speed trains. The speed is around roughly of 300 km per hour to 500 km per hour. So yes, it is possible, but they have implemented in a different way. So how they have implemented, the idea was they have proposed, like, instead of serving, like in a train or in a mobile, there are so many users, they want to communicate with the base station. So rather base station serving all these users, beamforming all these users, there will be a kind of access point in the centrally located in the mobile, like your train, high-speed train, and the base station will solve that particular access point. And through that access point, again, there will be like small Wi-Fi routers, or there will be small access points can be created inside each compartment, and through that the users can be served. So ideally, it is not designed for serving all the users directly, but through some access point in that way.
Okay. So, Professor Abhay, I have a few final questions before we wrap up the session for today.
Sorry, Amrita.
Yeah, Prem. Oh, sorry.
Yeah,
please go ahead.
Okay. Thank you, Professor Abhay, for the interesting talk. I have one question. Like, you showed the largest realization of Massimaimo.
Yes.
So yeah. So those results you showed, was those for 5G or 4G?
Okay, this is for 5G only, but the configuration they have chosen for 4G, so that they can compare the difference. Like 4G, like if you compare 5G and 4G maximum bandwidth they can support up to 20 megahertz, but 5G it can go 100 megahertz, and if you are going for FR1 and FR2, it can go up to 400 megahertz as well. But they have chosen to be on the all these parameters with the 4G side, except only changing the number of antenna and the operating frequency of the 5G band.
Okay, and then I believe these results are for FR1, not for FR2.
Yeah. These are for FR1. These are for FR1. Not
so
for
any idea, any results available in public for FR2? Such kind of realization?
I don't think so. Like there are industry, they are doing experiments in the closed door, but I am not very aware of any such kind of realization for millimeter waves. So this is for FR1.
Okay, thanks for the information. Yeah. Okay, yeah, over to you, Amrita. Thank you.
Yeah, so Professor Abhay, we have another follow-up question from Neeta.
Yes.
What will be the impact of correlation between antenna elements at the base station?
Yes, so definitely the correlation will impact the performance. There is no doubt about that, and therefore I talked about this λ/2 separation, and that separation needs to be maintained so that we will have a minimum amount of the correlation between the antennas, so that all the channel paths are independent. And therefore we are talking about the current whatever the realizations I'm talking about, they are mostly, most of the products are up to 64 antenna, and maximum this is 120 antenna. But if you go bigger than that, you need even larger size, and that cannot be deployed in the current base stations, and we need a future extension. That's why we talk about all those extensions.
Right, right. So, okay. Any other questions from the audience?
Yes, Professor Abhay, I have a follow-up question.
Yes, please.
Can you show your performance comparison plot with ML detection and the machine learning based detection? I think you have compared the optimality also. Yes.
This one you are talking about?
Yes, this one. So my question is, when we study the digital communication, the MAP or ML detection is the optimal one as far as theoretical sense. Now my question, on what background the BDNN has performed better compared to the ML detection, and why?
Okay, good that you have asked this question. I was thinking, but no one has asked. Okay, let me answer this. So what happens, like all these ML detections, like they are mathematically proven that they can do the best, but there are some underlying assumptions. What are the assumptions that we have made for proving that ML will perform optimally? That all the bits are equally likely, then the noise distribution is Gaussian, all such kind of assumptions we made. Then we arrive at this result that ML is the best. For block-based DNN, it like any ML detection, it depends on like what is your input and output, what is your reference point on which you have trained. So in this, we are not used ML to train our DNN model. We have used the actual input signal itself to train the model. That's in the training phase, we assume that we know whatever input we have used for generating the signal. So it's kind of a reverse direction. So we are not using the ML output for training that model. So that's why we are able, like this DNN model is able to track the other non-linearities or other properties of the signal that we have not assumed, or we have assumed idealistically in ML. So that's why
at the receiver end, how can we assume XIs are available in order to fit?
Okay, so it's a training phase. It's kind of an offline. It's not something you are doing online. So you like, it's a kind of a, you can design some like training signal, and we can assume that the same training signal is known at the receiver also. That is not something which is like kind of impractical. We can do that. Like it's kind of a pilot, like you transmit a pilot signal and we assume that receiver also know the pilot signal, and based on that we do the channel estimation. So on a similar note, we can do for signal detection also. We can have a predefined set of transmit signal, and we can assume that these are the transmit signals that are used to generate this particular receive signal. And for that, we can use to train our DNN model. So that we have done.
Okay. And when shall we use the DNN model, and when shall we switch to the conventional model as far as complexity and performance point of view?
Okay. This is not something like a very well-defined. I do not have any very well-defined answer for that. I'm still exploring like what are the like limitations and when we should go. Personally speaking, we should go for a like there are two extremes. One extreme is that everything is based on the conventional model. The other extreme is that everything is based on the block, like all the DNN based model. Both the extremes may not be a good options moving forward. We should have like going forward means when we have the future systems where we have more number of antenna. So some problems which are difficult to track, those problems must be solved through the DNN based model, and those problems which we can solve through the conventional approach at a lower complexity, that should remain as it is. That is my personal view, but there is I do not have a well-defined answer for that.
Thank you. Thank you. Professor Amrita, please go ahead.
Yeah, so I also had the same question. I think Professor Priyanka, yeah.
Ma'am, just one moment.
Sure. Sorry, Divakar, please go ahead.
Yeah, just related to the previous question.
Sure.
So the offline training, how are you getting the real channel conditions basically? Then if you're doing it offline.
Okay, offline, I do not mean that so what I mean by offline here is that we have not actually started the communication, like transmitting the information. This is like a pre-stage of before actually doing any communication. We have to train the model, and there everything is happening with wireless. But the only thing is that we assume that we know whatever input signal like we are transmitting is known at both the transmitter and receiver. Something similar to pilot.
Okay, so Professor Abhay, one last question from my side. Then I think hopefully we will wrap up the Q&A session. Everybody seems to be extremely interested in asking questions.
Right.
Yeah. So, Professor Abhay, the two methods of signal detection which you talked about, one is the deep encoder decoder framework, and the other one is, I understand, deep image prior. Am I right?
Right.
So, what are the trade-offs, I mean, the pros and cons of using each one of them?
Okay, so the deep image prior and deep decoder. Deep decoder is under parameterized model, and deep image prior is over parameterized model. So deep decoder, since it is under parameterized, so the complexity and the implementation complexity will be on the lower side. On the other side, deep image prior, which is over parameterized, so it will require a slightly higher complexity compared to the deep decoder. So that is the major difference between these two algorithms, and obviously deep image prior will give you the better performance compared to the deep decoder because it is over parameterized.
But both of them need to have a neural network kind of an architecture to work with?
Yes.
Okay. Because when we talk about prior assignment based any kind of an detection, as per my understanding in the conventional, say, compressive sensing kind of a thing, we start with a prior assumption and then we go on to deal with the problem.
Okay.
So, but I understand in the context of this deep image prior, which maybe has been applied to signal detection in a communication setup, you also need to go hand in hand with a neural network architecture.
Right.
Okay. Thank you, Professor Abhay. That's all from my side. Thank you so much for being patiently answering all our questions and for this extremely relevant and timely talk. I would now like to call Professor Jaya to thank the speaker and close Samvad session for today.
Thank you, Amrita. At the outset, let me thank Professor Abhay for such an informative talk and an even more exciting Q&A session. So this is a talk in the theme of a roadmap to 5G and beyond communication, as you're all well aware. We have one more pending talk by Professor Sridhar on September 13th. We are taking a break from this theme for next week because of Teachers' Day on Sunday. And we have our former director, Professor Sargopan, giving us a Samvaad-Talk on September 6th. So this talk is on online education, the missed opportunity, where he is going to highlight on how COVID-19 has affected education at large. With that, we kickstart our next theme as well, which is on education and technology. We could not get Professor Sargopan to give a talk at Samvad while he was a director. So now that he has retired in the end of June, early July, we get to have him on Samvad, right? So this is going to be a very interesting talk. So we welcome all of you for the talk and happy Teachers' Day in advance to everybody. Thank you so much. with that, we can close today's session.
Yeah. Thank you, Professor Jaya. Thank you, Professor Amrita. And thank you, entire Samvaad team at IIT Bangalore for inviting me. Thank you.